Shannon's second theorem deals with the amount of error-free information we can get through a channel. In order to appreciate more fully the significance of this theorem, let us look into the question of the error probability of a channel. For some of the simple channels which we have studied, such as binary symmetric channel and R symmetric channel, it is intuitively clear what it is reasonable to call the error probability of a channel. Nevertheless, in the simple cases also, the error probability of a channel is dependent upon a factor not yet discussed in the study of information channel. Let us consider a simple binary symmetric channel with the channel matrix as follows. Ordinarily, we would say that the probability of error of this channel is 0.1. Note, however, that this statement depends upon the assumption that the channel is being used in a reasonable manner. If the receiver were to examine the channel output and decide that a 1 was sent when a 0 is received and vice versa, the probability of error of this channel would be 0.9. Of course, this is not a reasonable use of the channel, but it is a possibility which we should also consider. The error probability of the channel depends upon how the receiver interprets the output symbol of the channel. To bring out this point in a more meaningful case, take the channel with a channel matrix given as follows. This channel has 3 inputs A1, A2 and A3 and 3 outputs B1, B2 and B3. When a particular channel output is received, which input should we say was sent? This question prompts us to the following definition. Consider a channel with an R symbol input alphabet identified as capital A is equal to the letters of the alphabet AI for I equal to 1, 2 up to R, and an S symbol output alphabet identified as capital B with the letters of that alphabet being Bj, where j is equal to 1, 2 up to S. Now, a decision rule defined as d of Bj is any function specifying a unique inputs symbol for each output symbol. In order to understand this definition in a more meaningful manner, let us take a simple example. Two possible decision rules for the channel which is given by this channel matrix. Let us indicate it by as equation 2 and this channel matrix as equation 1. So, two possible decision rules for the channels of channel given by this channel matrix are dB1 is equal to A1, d of B2 is equal to A2 and d of B3 is equal to A3. Another decision rule for the same channel could be as follows: d of B1 is equal to A1, d of B2 is equal to A3 and d of B3 is equal to A2. So, for a channel with R inputs and S outputs, there are R raised to S different possible decision rules. Therefore, the question which prompted our definition of this a decision rule may therefore be rephrased as which one of this RS decision rules should we use. Now, the answer to this question will depend upon what we are trying to accomplish, but a reasonable goal for our purpose is the minimization of the error probability of the channel. Hence, we seek a decision rule which minimizes the error probability of the channel. To find such a rule, we calculate the probability of error denoted by P E. Now, this probability of error may be written as the average of probability of E given Bj. This is the conditional probability of error given that the output of the channel is Bj. So, we can write the probability of error of the channel is Pa equal to summation of P of E given Bj multiplied by probability of B multiplied Pe is equal to summation of probability of E given B multiplied by probability of B summed over the alphabet B. As discussed earlier and without any loss of generality, we will drop the subscript j with B. Now, this equation expresses the error probability as a sum of non-negative terms. Therefore, in order to minimize the probability of error by choice of a decision rule dBj, we may select dBj to minimize each term in the sum separately. Now, probability of Bj does not depend upon the decision rule we use. So, it is equivalent to choose dBj to minimize the conditional probability of error, that is P of E given Bj. So, for a fixed decision rule, that is d of Bj equal to some ai, probability of error given Bj is equal to 1 minus probability of d Bj given Bj. Now, since our decision rule is fixed, probability of dBj given Bj is the backward probability, that is probability of ai given Bj. So, in order to minimize this equation for each Bj, we choose d of Bj equal to A star, where A star is defined by probability of A star given Bj is greater than or equal to probability of Ai given Bj for all i's. Let us denote this equation by 7a and this by 7b. So, in other words, the channel error probability is minimized if we use that decision rule which chooses for each output symbol the input symbol with the highest probability. Now, this decision rule is sometimes called a conditional maximum likelihood decision rule. The conditional maximum likelihood decision rule depends upon the a priori probabilities P of AI. So, we may use Bayes' law to write this equation 7b as probability of Bj given A star multiplied by probability of A star divided by probability of Bj. This should be greater than or equal to probability of Bj given Ai multiplied by probability of Ai divided by probability of Bj for all i's. Hence, when all the a priori probabilities are equal, the conditional maximum likelihood decision rule may be written as d of Bj is equal to A star, where probability of Bj given A star is greater than or equal to probability of Bj given Ai for all I. The decision rule defined by this equation 9b is known as the maximum likelihood decision rule. The maximum likelihood decision rule does not depend upon the a priori probabilities. So, when the a priori probabilities are all equal, the maximum likelihood decision rule results in a minimum value for the probability of error. Even if the a priori probabilities are not equal, or in those cases where these probabilities are unknown, we could still employ the maximum likelihood decision procedure, but in such a case we may not be assured of obtaining a minimum value of the channel error probability. Let us take the earlier example which we had discussed. For this channel matrix, now we can write a maximum likelihood decision rule as follows: d of B1 is equal to A1, d of B2 is equal to A3, and d of B3 is equal to A2. Now, it is important to note that this rule is not unique. There are in fact 3 maximum likelihood decision rules for this channel. Now, the error probability using any given decision rule is easily obtained with the help of equation 5 and equation 6 as follows. Probability of error is equal to summation of probability E given B, probability of B summed over alphabet B. This is equal to probability of B summation summed over alphabet B, capital B, that is, minus probability of D B given probability B summed over alphabet B, which can be simplified as 1 minus summation over capital B probability of D B comma B. The terms in the summation of this equation number 10 are just the joint probability that d b j is equal to A star is transmitted and B j is received for each j. Hence, defining probability E complement as 1 minus probability P E, we can write P bar E is equal to summation of probability A star B summed over B. Now, we know that summation of probabilities, that is joint probability A B over alphabet A B is equal to 1. So, using this relationship, we can rewrite the equation number 10 as follows. Probability E is equal to summation of joint probability of A B summed over the alphabet B and A minus A star. The notation summation A minus A star is meant to indicate that this sum is over all members of the A alphabet except D B j is equal to A star. So, an alternative way of writing this same equation number 13 is probability of E is equal to probability of B given A multiplied by probability of A. Now, if we assume that the a priori probability, that is P A, are all equal, then this equation can be written as P E is equal to 1 by R summation over capital B capital A minus A star probability of B given A. Now, this equation is of some interest, since for the special case of equal a priori probabilities, it provides an expression for the channel error probability in terms of a sum over the elements of the channel matrix P B given A. Now, this sum is over all elements of the channel matrix except that one term corresponding to D of D j, which is omitted from each column. Now, for the same channel matrix which we considered earlier, that is this channel matrix, if we assume that all the 3 input symbols, that is A1, A2, A3 are chosen with equal probabilities, then we can apply a maximum likelihood decision rule, and if we use that maximum likelihood decision rule, then the minimum probability of error which we will get for such a channel would be given by using this equation as follows. Probability of E is equal to 1/3 summation over So, now we have studied how to find the error probability for a channel, but this we have done without reference to entropy or equivocation or mutual information. Now, we will see the connection between these two separate sets of ideas. As a first step in this direction, we will derive upper and lower bounds on the equivocation in terms of the error probability of a channel. So, in our derivation to follow, we shall make repeated use of these two equations which we derived earlier, that is P complement E is equal to summation of joint probabilities A star B. This was equation number 11, and probability of E equals summation of joint probabilities A B summed over alphabet B and A minus A star. This was equation number 13. Using these two relationships, we construct the identity H of P E plus P E log to the base 2 of r minus 1 is equal to probability of error log of r minus 1 upon P E plus P complement log of 1 by P complement E. This can be rewritten using these equations as follows. Probability A B log of r minus 1 upon probability of error plus this term can be rewritten from this expression as probability A star P log of 1 by probability complement probability error summed over alphabet B. Now, the equivocation, that is H of A given B, is by definition we have seen equal to summation of probability A B log of 1 by probability A given B summed over B and A alphabet. Now, this equivocation, that is H of A given B, can be also written in terms of the same sort of summations which we have written in this equation number 17. So, if we follow the same procedure, we can write H of A given B equal to summation of joint probabilities P A B log of 1 P A given B summed over B A minus A star plus summation of P A star B log of 1 by P A star given B over alphabet B. Now, if we subtract this equation, that is equation number 17 from equation number 18, then we get the relationship as follows: H of A given B minus H of probability of error minus probability of error log to the base 2 r minus 1 is equal to summation B A minus A star probability of A B log of probability of error divided by r minus 1 into probability of A given B plus summation over alphabet B of probability of A star B log of P complement divided by probability of A star given B. Now, these logarithms are to the base 2. So, if we change the base of the logarithm by using the following relationship, log of A x is equal to log B x upon log of A to the base B, we can rewrite equation number 19 in terms of natural logarithms as follows: log of E inverse H of A given B minus H of P E minus P E log r minus 1 equals probability of a p natural logarithm of p e divided by r minus 1 probability of a given p summed over alphabet b minus a star plus summations of probability a star b log of p complement over p a star b over the alphabet b. Now, the advantage of writing in the natural logarithm is we can use the inequality which we had seen in our earlier lectures, that is log of x is always less than equal to x minus 1. So, if we use this inequality, then we can write each term in this summation on the right hand side of equation number 20 as follows: summation of probability a b summed over b minus a star. We apply this relationship to the quantity as shown here, will give us P E r minus 1 probability of a given b minus 1 plus summation probability a star b complement P E upon probability a star b minus 1. Now, this can be, so the right hand side of the expression of the equation number 20 can be shown to be less than equal to this summation, and this can be further simplified as P E over r minus 1 summation of probability b minus probability of a b b a minus a star plus p complement summation of p b b minus a star b summed over b. Now, this quantity is equal to probability of E, and this quantity is equal to p complement E. So, if we substitute P E for this quantity and p complement for this quantity and then further simplify this, then this equation number 22 will reduce to 0. So, what we have shown that this quantity on the left hand side is less than equal to 0. So, what it implies is that h of A given B is less than equal to h of P E plus P E log of r minus 1. So, this is the inequality we wanted to derive, and this important inequality which relates the probability of a channel probability, this inequality which relates equivocation to the error probability of a channel was first derived by Fano, and it is known as Fano's inequality. It is useful for proving the Shannon's second theorem in a very general case. Now, this inequality is valid no matter what decision rule we use, although the error probability can depend drastically upon the decision rule. Now, this inequality has a very interesting interpretation. The average uncertainty about A, if B is known, that is this quantity, can be regarded as the uncertainty of whether an error has been made or not, and if an error has been made with probability P E, then the uncertainty of which of the r minus 1 remaining symbols has been transmitted. Now, the first amount of uncertainty, that is this quantity, is given by h of P E, while the second is at most equal to log of r minus 1 weighted with the probability of error, that is P E. So, from this inequality it follows that a small average error probability means that equivocation is also small. Now, the inequality is depicted graphically as shown here. So, h of A given B will be always lying below this curve. This curve is given by h of P e plus P e log r minus 1. For P e equal to 1, the value would be log r minus 1, and for P equal to 0, h of A given B would be obviously equal to 0. So, this is the relationship we have between error probability and equivocation. Now, let us examine the condition for equality in the Fano bound, which is given by this equation. Now, the inequality log x less than or equal to x minus 1 becomes an equality if and only if x is equal to 1. So, if we use this condition in this equation, we find that the Fano bound becomes an equality if and only if probability of P A given B is equal to P E divided by r minus 1 for all B and A not equal to A star, and probability of A star given B is equal to P complement E for all B. So, if these two conditions are satisfied, then we would get the equality in the Fano bound. Now, since probability of P A given B summed over A is equal to 1 for all B, it implies that the second condition, that is this condition, follows from the first condition. So, this equation probability of A given B is equal to probability of E r minus 1 implies that for each B, all input symbols except the only, it implies that for all input symbols except the one selected by a decision rule are equiprobable. Now, this condition thus serves to reinforce our interpretation of the Fano bound. The objective of Shannon's second theorem is to describe the fundamental limitations on the transmission of reliable error-free messages through an unreliable channel. In the next class, we will initiate our discussion on the procedure to obtain error-free communication over noisy channel.